starting on nitrogen to ammonia conversions, we were very focused on this energy storage problem. We weren't thinking about problems overseas or problems that were affecting the developing world. And this is something that came out of interactions here at MIT, that I really started to understand that there are ways in which the ability to convert nitrogen to ammonia may actually be more significant in the context of being able to produce fertilizers to actually have some impact on problems that I think I grew up hearing about, and I'm sometimes very sad to see that they still stand in a very similar place when it looks at something like hunger, right? That it's something that you sometimes start to believe that maybe there's really nothing that I individually could do something about this, right? But when I talk to my students and when I wake up in the morning myself, you wake up with a sense of excitement, right? That these technologies that we're building could have a meaningful impact. And those are things that come out of the ecosystem, right? We, as academics, pride ourselves on ideas, but those ideas are really something that become even more powerful in the context of a community. And you have an idea, you share it with a student, that student shares it with a friend, and then it comes back to you as something even more powerful. And this ability to convert nitrogen to ammonia is one example of that, both in terms of using it not just for energy storage, but as a method of producing fertilizers, but also in the way that we're doing it. We had certain visions about what we thought would work for this. It turned out, as our students were trying to work on it, that the initial plan that we had just would not have ever worked. But they have dreamt of ways in which certain catalysts interact with molecules and have used that to lay out an entirely different path, which is proving to be successful. And so we're very excited to be a part of this community in which these ideas move around and have a life of their own. So a smaller part of our research program is finding ways of utilizing natural gas to make it into something that can be moved around more easily or made into the materials and molecules that we interact with in our everyday lives. And so the boom in shale gas has been of great benefit to the United States in terms of improving our energy security, our energy independence. And so those are trends that we're very excited about. But we also need to find ways in which we can harness that resource more effectively and in a way that perhaps doesn't impact global warming as strongly. And so in that respect, we're interested in finding ways, for instance, of converting methane into methanol. That is a transformation which is very challenging to do. You're starting with CH4 and trying to make it into CH3OH, and you're just inserting one oxygen between a carbon and a hydrogen. It turns out that that's a very difficult transformation because when you convert methane into methanol, the carbon-hydrogen bonds in methanol are weaker than they are in methane. And so you end up reacting that methanol much more easily to something else, some undesired product, rather than reacting the methane into methanol. That's what you really want to be doing. So we're devising strategies to do this transformation more selectively. Nature is where we get inspiration for this. Methane monooxygenase is an enzyme that has the ability to take methane, convert it into methanol, and stop there. And the way it does it is by having this hydrophobic cavity within the enzyme that allows methane to be there, but makes it very difficult for methanol to hang around. So as soon as that methane becomes methanol, it gets rapidly excluded from the enzyme. It can't get converted any further. And so we're borrowing this concept of solubility, to make synthetic catalysts that can facilitate the transformation of methane into methanol. So we're hoping that this concept can help to provide a new paradigm for making natural gas into a condensable fuel. Methanol is great because it's a liquid. It's much easier to move a liquid around than it is a gas. And so you can just put it into a tanker and use a lot of existing infrastructure to export methanol, to use it here domestically. We think this sort of transformation will make the use of shale gas even more widespread and more valuable. Shale gas, one of the primary components of that is methane, and so we're focusing on that dominant component of shale gas to see what we can make that into. Yeah, so the problem with the natural enzyme is that if you want to scale this process up to be able to do it in a way in which you can convert a meaningfully large quantity of methane into methanol, that's where it starts to fall short. If you were doing a very, very small scale operation and your goal was simply to have very selective conversion, then you could certainly use the enzyme. But the enzyme starts to fall short when you try to envision a scaled up method of conducting this transformation. That's why we're interested in these synthetic analogs, which should be able to provide much greater throughput for the process. Yeah. And so when we look at the conversion of nitrogen to ammonia or CO2 to methanol, these are problems which involve many different, what we refer to as unit operations. There's the unit operation in which the exact reaction occurs. There are then downstream separations that are involved, for instance, in taking methanol and water, which are often produced together, to separate those into saleable products. There are unit operations that occur before the reactor to purify, for instance, the CO2, or to separate air into nitrogen and oxygen. And so there's a lot of industry expertise in these surrounding unit operations that we want to be able to bring in. And what we want to bring to the collaboration is an understanding of the reactor unit operation itself. That there are a lot of advances that we've made in terms of catalyst design and scale-up of these that would be greatly enhanced in the hands of a corporate or industrial partner who understands what this sort of process would look like when scaled up to even greater sizes than we've been able to. And so that understanding of scale-up for us is essential. That as chemical engineers, we understand this conceptually, but at the laboratory scale, we can only go so large. And so those partnerships help bring these ideas to be something that's physical and real at a larger scale.